Section 10.1, question P5, and we're starting to get into the real heart of inferential statistics here, excuse me. So we have men's body temperatures, and there is some variation in this. So even though you hear the 98.6 thrown out there a lot, it turns out that that tends not to, well, we're going to take a look at that, but it certainly isn't the exact body temperature, healthy body temperature for every male or female for that matter. So that's what we're looking at though, and we're trying to get a sense of, is it even a reasonable mean, or is it a little bit off no matter how you look at it? So we want to construct a 95% confidence interval, and in order to do that, we start off with the sample mean, and that's kind of our best guess estimate. So we had 122 men, got the sample mean, so that's going to be at the center of our confidence interval. But then we want to know how much flexibility are we going to go out into each direction, because we know that 98.1 is probably not the exact population mean, just because it's the mean of our sample here. And what we're trying to do is construct an interval where we think the population mean probably is. And even though we can't even be certain that it's in that interval, we want to be, in this case, 95% confident that it is in the interval. So to do that, we need to, I'm going to show you the formula here that we're working with. We start with the sample mean, and we're going to add and subtract this t-critical times the sample standard deviation divided by the square root of the sample size. These are all just plugging in the values. The real new thing here is this t critical t. How much are we wanting to go out in each direction? And before, we actually had a z. If you'll remember, we often used 1.96. Now, why can't we just keep using that? Well, we could, and it would really be a pretty good estimate, especially as we get a higher and higher sample size. But theoretically, we are using the sample standard deviation, not the population. You'll remember that sigma here. And because of that, we're using a slightly different distribution. It's very similar to the normal distribution, so that z was that normal distribution that we were working with, that bell-shaped curve. And t distribution is also bell-shaped, but it has a little bit more in the extremes. It's a little bit, if you overlay them, and there's another question that I'll let you look at that deals with the shape, but it's very similar to a z. Nevertheless, we still have to get this t value. So how do we do that? Well, one way we can use table B, look up. We have this degrees of freedom. So in our case, it's going to be 1 less than the sample size. So we're going to have, or I'm going to have 121 in my example with 122 people in the sample. And because we don't have an exact one on that table, the closest one is the 100 degrees of freedom, which if we look for a 0.05, we want 0.025 actually on each tail, so that it totals up to 0.05, and that's the risk of making a type 1 error, which we'll get into more, but that's going to give us, together with the degrees of freedom, will give us this value of t, 1.984. Now if we want a more precise, or if you want to use it a different way, we could use Excel, and in order to do that, we're going to use something called the inverse t. So instead of putting in a value that we're at, and then we want to know the probability of getting to the left of that, which is what we've done before in Excel, we can put in a probability, and it will tell us what value on the t distribution will give us that probability. And notice when I type in t.inv, I should have two options, either the normal inv or the .2t. And this is a two-tailed test. In other words, I'm willing to make an error either high or low. So when I'm building my confidence interval, I'm 98% or 95% confident that the mean will be in that interval. The other 5% could come 2.5% to the left. In other words, the real mean could be below my confidence interval, or it could be to the right. So that's why I'm using a two-tail. Whenever you use a confidence interval on something that's normally or approximately normally distributed, you should use the two-tail. So as soon as I hit my parentheses, it tells me to give the probability. Well, this is just the probability that how much error I'm willing to take. So by putting 0.05, I'm saying I'm willing to make a 5% chance of being wrong. Now, why wouldn't I want to be less? Why wouldn't I want to be a 1% chance, 0.01? I could, but that's going to give me a much less accurate, it's going to give me a much less, or a much wider interval, so it's harder to tell where the mean actually is. I might be confident that it's in that interval, but because it's so big, it's not very helpful. So 0.05 is a standard willingness of making a type 1 error here. And how did I get that? They want a 95% confidence interval, so I'm just subtracting. The 95% is my confidence, the 5% is the willingness to make a mistake. So I'm subtracting the 95% from 1. And then it asks me for degrees of freedom, so I can have 121 here. And that gives me 1.979. Notice that that's very similar to this 1.98 here. But it is a little bit different. And if I put that in, then I'll get my mean, my sample mean, plus or minus that little extra bit, which is my flex to the left and to the right of the mean. Okay, going back here, so we use that to get these two numbers. I'm not sure what this is. This is probably something coming from an original version of the question that they then deleted. But we are 95% confident that the true mean body temperature is between these two numbers. So this is just giving an interpretation of what the 95% confidence interval actually means or represents. Is 98.6 in this interval? In my interval, it's not. It may be in yours, but mine goes up to 98.23, so it's not in that interval. Because it's not in that interval, I'm going to say that the mean body temperature of men is probably less than 98.6 degrees. In other words, that projected average temperature doesn't seem to be fitting well with the data we're actually getting. The data we're getting suggests that the real actual mean temperature, body temperature for men, is somewhere between high 97s and 98.2. Now we're not certain. Again, that's that 5% willingness to make an error because we only have a 95% confidence interval. But it's usually good enough evidence to say that no, the mean body temperature probably is not 98.6 degrees.